Hello guys, welcome to another episode of CUDA Education. Today we are continuing our path of investigating transparency and transparency layers. So when we run our default application, just to recap, we get our layers correctly sort of rendered behind the initial closest layer, right? But then once we start to play around with this number, so let's say we just do 2, we're going to see that things start to miss. So we basically just have this one layer recognized and the default. This last layer is a default, so it doesn't really count. But we just see this one layer in the transparency that's recognized, and all the other layers disappear, right? So anyway, I don't want to, that's just a recap to anchor you guys if this is the first video in the series. But if you want to do this correctly, just look at the label of the video and go back to the first video in the series. I have a numbering system that helps to understand all that's going on. So anyway, what we want to do is just, in detail kind of go through what happens after we set this layers number here, right? So number of transparent geometry layers that the app stores in image block memory. Each layer consumes tile memory and increases the value of the pipeline's image block sample length property, right? So that's where we get this for. So I want to just do like the first 3 steps after this. It gets more and more involved, but let's just do a small investigation of what happens after this, and the idea is that you guys will be able to follow. So we have starting at line 59, knum layers for defines how many transparent fragments per pixel the image block can retain. Okay, what happens next in this file? Transparent fragment values uses knum layers in line 66, so this guy right here. The struct allocates 2 arrays of that size. So it allocates color and depth. And remember, we talked about how, each one of these window panes, it has a color associated with it and it has a depth associated with it. Depth as it relates to where the camera is, right? So we're going to see that so each pixel gets storage for 4 transparent layers. Color of each stored fragment, depth of each stored fragment. Okay, so let's just go through this little piece right here. So it's transparent fragment values, which is this guy right here. So it's a strut called transparent fragment values. Stores color and depth values of transparent fragments. The process transparent fragment shader adds color values from transparent geometries in ascending depth order. Then the blend fragments shader blends the color values for each fragment in descending depth order after the app draws all the transparency. All right, let's not get too much into that. Let's just focus on this transparent fragment values struct. So it is a struct and it has 2 things in it. So this is the entirety of the struct right here. And a strut is like an array. It's like something where you have a structure to it and you store stuff in it, right? So we have 2 things. We have this thing right here, colors, and we have this thing right here, depth, okay? So store the color of the transparent fragment. Use a packed data type to reduce the size of the explicit image block. Okay, so, right now we're just building a strut. We haven't actually gotten to the image block stuff yet. So we have a strut of basically colors, right? And it has basically, this colors thing has, it's taking in the number of layers that we have. So for our case, it's 4, right? Because that's the default value for the application. So it's 4, which we set up here, right? So it has 4 layers. So for each window pane, it's basically storing the colors of each one of the 4 window panes that we have. And then it also has an array of transparent fragment distances from the camera. So we have depth values and we have a depth associated with each one of the window panes in our application. So 1, 2, 3, 4, we have a color and a depth associated with it from the camera, right? So this is just one strut. This is the transparent fragment value strut. let us just reread it again. Transparent fragment values uses k-num layers in, this file. The strut allocates two arrays of that size, right? So it's an array, a colors array of four items, and a depth array of 4 items, again corresponding to the window panes that we have. All right, so this is our first strut. We kind of understand this, and we could move on from here. All right, so the next thing that we do, transparent fragment store, puts the strut into image block memory. So now we have our strut here, but now we have to put it into image block memory. So it's sort of like, it's like a package within a package. So you're basically taking this strut right here, right, which is just an array, 2 arrays, one of color and one of depth, right? So it's 2 arrays, and each one of the arrays has four items in it, 4 slots in it for each one of the window panes that we have, right? And then now we're taking this package and we're putting it into transparent fragment store, puts that strut into the image block memory, line 79. This wrapper marks the data with image block data, right? So basically, store the color values for multiple fragments in image block memory, right? So this is now we're getting into the image block memory, which is something kind of sort of proprietary to Apple, which I discussed in the previous episode. So the image block data attribute tells Metal to store values in the GPU's image block memory, which preserves its data for an entire render pass, right? So we have our transparent fragment values here, which is a strut. And then notice that we have transparent fragment store, but inside of it we have transparent fragment values and then, the values, right? So that's, that variable, that values variable is we'll investigate that, but basically it's a variable values of type transparent fragment values, right? And then we're making sure that it goes into image block data. I don't want to get bogged down with the syntax too much right now. Let us just focus on the big idea. We will get into syntax, I'm sure at some point, but let us just kind of focus on what the big idea is. So again, this transparent fragment store puts the strut into the image block memory. That is the actual per pixel tile memory storage used across the render pass, right? So for each pixel, per pixel tile memory storage used across the render pass, right? So, each pixel is going to have, it's going to have, that is the actual per pixel tile memory storage used across the render pass. So, each pixel is going to have all of this information in it, color and depth value, and basically, for all 4 of the window panes, right? So each pixel is going to have that. So we're basically taking this strut and we're putting it into image block memory. Store the color values for multiple fragments in image block memory. The image block data attribute tells Metal to store values in the GPU's image block memory, which preserves its data for an entire render pass, right? So that's this guy right here. All right, and then we go to number 3. The tile shader clears all k num layer slots in line 85. Init transparent fragment store runs once per tile / pixel location and loops from 0 to k num layers -1. For each slot, it writes 0 and infinity. That means every slot starts as empty, right? So this is for init transparent fragment store. Initializes, so let's look at the actual code and what it says. Initializes an image block structure to centennial values, right? So init transparent fragment store. So we have image block transparent fragment values. Where did we see that before? Up here. Init, so image block transparent fragment values, image block layout explicit, block data, use your local thread ID, thread position, and thread group. Yeah. all syntax, guys. This is all syntax. But what we want to focus on now. So all of this is this init transparent fragment store. All of this right here, from here going down to here. Okay. So this is init transparent fragment store. Again, what we want to do. Right, it's basically clearing out the slots with this guy right here. So we're looping through the layers, and we're setting, we're setting the default color, a default color, and basically setting the depth to infinity. So it's sort of, it discards everything. I believe this color right here is actually, this guy right here. So you see this guy right here? Right, this guy right here, right? I believe it's this guy, because in the previous episode we played around with it, and that was sort of the initial setup, right? And then we set the depths to infinity, which effectively means that we disregard it, right? Because it's way out in the distance, so we disregard it. This is what I want to focus on for right now. So we loop through the thing, and we zero out everything so that we get so we have 0 and we have depth of infinity. That means every slot starts as empty. Okay. And then we go to our last part for this episode, where we start talking about so part 4 now. So we have an image block structure here. So let's go to part 4. Each transparent fragment tries to insert itself into those k num layers slots. So 100. Adds transparent fragments into an image block structure in depth order. So let's just go through this. Each transparent fragment tries to insert itself into those k num layers slots. So line 100, process transparent fragment is called for each transparent fragment. Key steps: it computes this fragment's color and depth. It loops over the stored layers from nearest slot index to farthest, right? So that's going to be line 116. For each slot, it compares the new fragment depth with the stored depth. If the new fragment is nearer, it inserts it into the new fragment. If the new fragment is nearer, it inserts the new fragment into that slot and pushes the old one down to the next slot. This is basically an insert sort over a fixed size array. So with k num layers equal 4, the shader keeps the nearest 4 transparent fragments for that slot. Anything beyond 4 is dropped. So yeah, we're gonna just stop here. All right, so let's look at it. So we have process transparent fragment. We have a whole bunch of syntax which we're not really familiar with right now. So we get the fragment distance from the camera. So depth equals in Z and W. Insert the transparent fragment values in order of depth, discarding the farthest fragment after the colors and depths are full. So we loop through the layers again. So if depth is less than or equal to layer depth, so this layer depth, where is this layer depth? So if depth is less than layer depth, fragment colors insert, final color, layer color, depth, insert, layer depth. And then final color is layer color, final color, Depth is insert layer depth, depth, out, fragment values, return out. All right, so this is all syntax, which we're gonna have to dive into at some point. But let us just read this fourth part again. Each transparent fragment tries to insert itself into those K. Right. Each transparent fragment tries to insert itself into those K num layers slots. Right, line 100. Process transparent fragment is called for each transparent fragment. Key step, it computes the fragment's color and depth. Okay. It loops over the stored layers from nearest slot index to farthest. For each slot, it compares the new fragment depth with the stored depth. If the new fragment is near, it inserts it into the new fragment. It inserts the new fragment into the slot and pushes the old one down to the next slot. This basically is an insertion sort over a fixed size array. So with k num equals 4, the shader keeps the nearest 4 transparent fragments for that pixel. Anything beyond 4 is dropped. So yeah, we're gonna have to go through, we're gonna have to go through the syntax and all that's going on here, but we could kind of follow that. We're testing for depth here, and then we're inserting stuff, new information, right? Insert the transparent fragment values in order of depth, discarding the farthest fragments after the colors and depths are full. So that's pretty much where I want to stop for today. I know this is a tough episode, guys. I'm not going to put it any other way. It's a tough episode, but we need to actually go through all that's actually happening, because it's important. It's important for the it's important for us to understand what's happening. So we have our num layers of 4. We have our transparent fragment value strut, which includes colors, an array of an array with 4 slots for colors and an array with four slots for depth, right? And we have it in our strut here. We take that strut and then we basically associate it with image block. So we know we're doing image block memory stuff, right? With this guy right here. We basically collapse it into an image block memory. We do an initialization step, which basically means we're resetting all of our values. So all of this right here, we're resetting all of our values. We're emptying out, we have to have an initialization structure, initialize an image block structure to centennial values. So we have to initialize things to a default color, and then also the depth is infinity. So it is like way out, which means it's empty, right? And then we add transparent fragments into an image block structure in depth order, right? So we're basically adding in the fragments. We're looping through the we're finding out what the depth is of the fragment that we're considering. We're looping through each of the layers, and then we're seeing if the depth is less than the layer depth, and if it is, then we push it in, and then that effectively pushes out. It like pushes it down. It's like a pipe or some kind of So if we push something in, then everything else gets moved down, and we only consider the first 4, right? And we do some color calculations and all of that for that, and that's pretty much it. I don't want to get too much more in detail with this, but I think this is this gives us a better understanding of what's going on. Again, we'll get into the syntax, guys. Don't worry about the syntax. Just kind of understand the big picture idea. We will eventually get a better understanding of all that's going on, and I'll probably start tinkering with the syntax to see if we can mess things up and see a different result. This is the application again for you guys that just want to have an understanding. We care about the order independent transparency, which basically means that we do correct transparency starting from back to front, and we're not allowing for any random processing of how the transparency work, right? Obviously, if we go to unordered, then we get crazy stuff, but we're focused on the order independent stuff, which is the correct back to front. The back window pane to the front window pane. I don't think this window pane right here doesn't count. The last one is just the default, right? So again, guys, you could download this. There's a link down below for the code. If you're running Apple Silicon, you pretty much get Xcode, download the application, press the play button. And you'll get one initial error which basically says you got to run locally or something, and you basically can run the application and see all of this that's happening here, right? So we're in the renderer, shaders, APL shaders, and then, well, this is a function that we're currently in. So we get a whole bunch of stuff going on here. Okay, but that's it, guys. That's it. Thank you for watching. This is CUDA Education. You know what to do as it relates to helping the community and everything. Have a great day.